It hangs in our sky as a symbol of constancy itself, a silent, silver witness to the whole of human history. From the first moment our distant ancestors looked up in wonder, the moon has been our anchor in the cosmic ocean. It has guided mariners, inspired poets, and governed the rhythm of the tides, a dependable partner in a celestial waltz. But what if that constancy is an illusion? What if the dance is changing its tempo, slowly, almost imperceptibly? What if our nearest celestial neighbour is sending us a message, not in light, but in gravity, a warning whispered across the 250,000 miles of empty space that separates us? Recently, within the quiet corridors of NASA and the world's leading oceanographic institutes, that whisper has grown louder. A new understanding is dawning, built on decades of data, culminating in a stark and ominous forecast for our time. The moon, our eternal companion, is moving. And this subtle shift in its cosmic station is about to have profound consequences for life on Earth. This is not a sudden, violent lurch from its orbit. It is a slow, deliberate and relentless departure. An ancient process, written into the very laws of physics that bind our two worlds together. For as long as the Earth has had oceans and the moon has pulled upon them, this cosmic separation has been underway. But now something is different. Humanity has added a new, powerful variable to this equation, and the convergence of this ancient celestial cycle with our modern planetary crisis is setting the stage for a dramatic acceleration of change, a change that will redefine the coastlines of our world. To understand this prediction, we must first journey back in time, not just decades, but millennia, to our earliest attempts to comprehend this relationship. Ancient civilizations saw the moon as a deity, a mysterious lantern that governed the night and seemed to hold a strange power over the waters. The Babylonians meticulously charted its phases, the Greeks theorized about its nature, but the true mechanical link remained elusive, a piece of magic just beyond reason's grasp. It was not until the towering intellect of Isaac Newton in the 17th century that the spell was broken. With his law of universal gravitation, Newton revealed the invisible threads connecting Earth, Moon, and Sun. He explained that the tides were the oceans responding to the moon's gravitational caress, a colossal bulge of water pulled across the surface of our spinning planet. Yet even Newton's genius did not grasp the full story. His was a perfect clockwork universe. He did not foresee that the dance itself was draining energy from the system, that the partnership was not eternal. The first hints of this deeper truth came much later, with the painstaking work of astronomers studying ancient solar eclipses. They noticed a discrepancy. The timing of eclipses recorded by ancient civilizations did not perfectly match the predictions based on our current orbital models. Something was amiss. The only explanation was that, in the past, the Earth must have been spinning faster, and its days were shorter. The celestial clock was slowing down. But why? The answer lay not in the sky, but in the water. Imagine the Earth as a spinning figure skater. The moon's gravity pulls on our planet's oceans, creating two tidal bulges on opposite sides of the globe. Because the Earth rotates much faster than the moon orbits, these bulges are dragged slightly ahead of the moon's position. This displaced mass of water acts like a gravitational handle. The moon pulls back on this leading bulge, creating a braking effect, a constant gentle friction that slows our planet's rotation. The energy lost from Earth's spin has to go somewhere. Physics demands it, and it is transferred directly to the moon. This transfer of angular momentum acts like a persistent cosmic push. It boosts the moon into a slightly higher and therefore slower orbit. It is a paradox of orbital mechanics. To speed up in orbit is to move further away. For billions of years, this process has continued. The days on Earth have grown longer, and the moon has spiraled outward, its retreat measured in geological time. For most of human history, this was a theoretical concept, an astronomical curiosity. Then came the Apollo program. When Neil Armstrong and Buzz Aldrin set foot on the lunar surface in 1969, they did more than leave footprints. They deployed an experiment that would change our understanding of the Earth-Moon system forever. It was the Lunar Laser Ranging Retroreflector Array, a seemingly simple device, a panel of specialized mirrors designed to bounce beams of light directly back to their source. For over 50 years, observatories on Earth have been firing powerful laser pulses at these and subsequent arrays left by later Apollo missions. By measuring the round-trip travel time of these photons of light, down to the picosecond, scientists can calculate the distance to the Moon with astonishing millimeter-scale precision. And the data from these decades of measurements is unequivocal. The Moon is receding from the Earth at a rate of approximately 3.8 centimeters, or about 1.5 inches, every single year, about the same speed at which your fingernails grow. It seems like an insignificant distance, a triviality on a cosmic scale, but it is not. This is not a measurement of a single year, but the confirmation of a relentless cumulative process that has been unfolding for eons. And this slow departure is intimately connected to another, more complex lunar motion, a rhythm that is now at the heart of NASA's grave new forecast. The Moon's orbit around the Earth is not a perfect flat circle, like a disk on a table. It is tilted by about 5 degrees relative to Earth's own orbit around the Sun. Now visualize this tilted orbit not as a static path, but as a wobbling celestial hula hoop. This slow, powerful gyration is known as Lunar Nodal Precession. The entire orbital plane of the Moon wobbles like a spinning top that is starting to slow down. One full wobble of this massive invisible hoop takes precisely 18.6 years to complete, and this long, patient cycle has a direct and profound impact on the tides here on our world. For half of this 18.6-year cycle, during the downswing of the wobble, the Moon's gravitational alignment with the Earth and Sun results in tides that are suppressed. High tides are a little lower, and low tides are a little higher. The overall effect is muted, a period of relative coastal calm. For the other half of the cycle, the upswing, the opposite happens. The specific alignment of the Moon's wobbling orbit amplifies its gravitational pull on our oceans. High tides become significantly higher, and low tides become even lower. The tidal range expands and the power of the sea is magnified. Throughout human history, this 18.6-year rhythm has been playing out, a gentle, largely unnoticed pulse in the planet's oceans. Coastal communities would experience periods of more frequent minor flooding, followed by years of relative quiet, without ever truly understanding the celestial mechanism driving the change. The cycle was a background signal, lost in the noise of storms, seasonal variations and local weather patterns. But that is no longer the case. Because we have now introduced a deafening new sound into the planetary orchestra, global sea level rise. For the last century, and with terrifying acceleration in recent decades, our oceans have been steadily rising. Fed by the melting of glaciers and ice sheets in Greenland and Antarctica, and expanded by the thermal warming of the seawater itself. The baseline sea level is a new and powerful reality. Every coastline on Earth now starts from a higher launching point. The ocean is already closer to our doorsteps, and this is where the pieces of NASA's predictions snap together with chilling clarity. In the mid-2000s, the Earth is set to enter the next tide-amplifying phase of the 18.6-year Lunar Nodal Cycle. But this time, the lunar wobble will not be adding its push to the tides of the 20th century. It will be amplifying the tides of a world already transformed by a significant increase in baseline sea level. It is a force multiplier. A cosmic alignment converging with a man-made crisis. The gentle pulse of the past is about to become a hammering blow. A team of scientists led by the NASA Sea Level Change Science team at the University of Hawaii has modelled this convergence. Their research, published in the journal Nature Climate Change, was not speculative. It was a data-driven forecast based on the known physics of the lunar cycle and the measured reality of rising oceans. Their conclusion forms the basis of the ominous prediction. They foresee a dramatic and rapid increase in the number of high-tide flooding events, sometimes called nuisance floods or sunny day floods, for nearly all coastal cities in the United States and, by extension, around the globe. The term nuisance flood is deceptively mild. It fails to capture the corrosive, disruptive and relentless nature of these events. These are not floods born of hurricanes or torrential rain. They happen on perfectly clear, calm days, when the sky is blue and there is no hint of a storm. They are driven solely by the inexorable pull of the tides. Water will begin to well up from storm drains, pushing salt water into streets hundreds of meters from the shoreline. Roads will become impassable, not for hours during a storm, but for parts of every day, for weeks at a time. Think of the implications. For a resident of a city like Miami, Florida, or Norfolk, Virginia, this means a fundamental reordering of daily life. Commutes to work will become impossible during high tide. Parking garages will be inundated. Businesses will have their entrances blocked, their supply chains disrupted. The salt water is not just water. It is a corrosive agent. It will seep into the foundations of buildings, degrading concrete and rusting rebar. It will infiltrate underground infrastructure, shorting out electrical systems and contaminating freshwater aquifers. The very ground beneath these coastal cities will be silently poisoned from below. The researchers predict that these flooding days will not be spread evenly throughout the year. Instead, they will cluster together, creating month-long periods of chronic recurring inundation. Imagine a city where, for a full season, the basic functioning of urban life is held hostage by the tide charts, which will have to be consulted as frequently as the weather forecast. The economic toll will be immense, measured in lost productivity, damaged property, and the astronomical cost of remediation. But the social cost may be even greater. The constant stress, the financial ruin for small business owners, the slow-motion destruction of entire neighbourhoods. This is not a distant abstract future. The transition is expected to begin around the year 2030 and become a widespread, undeniable crisis by the mid-2030s. The movement of the Moon, its stately 18. 6-year Wobble is acting as a switch, flipping our coastal systems from a state of occasional inconvenience to one of chronic systemic failure. It has taken a natural rhythm and, by overlaying it on our altered climate, turned it into a weapon against our own infrastructure. The prediction is ominous because it is not about a single catastrophe, but about a new, grueling and permanent reality. A state of siege where the enemy is the sea itself, empowered by our celestial partner. And the long-term recession of the Moon, the 3.8 centimeters per year, plays a more subtle but equally profound role in our planet's destiny. This gradual distancing has been happening for over 4 billion years. When the Moon was first formed, likely from the debris of a titanic collision between a Mars-sized object and the proto-Earth, it was perhaps 10 times closer than it is today. It would have appeared monstrous in the sky, a giant looming orb. The Earth was spinning much faster, with days that may have been only 5 or 6 hours long. The tides would have been cataclysmic, 1,000-foot walls of water scouring the planet's surface. It was the Moon's gravitational braking, the very process that pushes it away, that slowed our planet down, stabilizing its rotation and making it more hospitable. The Moon acted as an anchor, preventing our planet's axis from wobbling chaotically, which would have led to wild, unpredictable swings in climate. Our satellite is, in many ways, the reason complex life was able to flourish here. It is our planetary stabilizer, our protector. But as it continues to drift away, its stabilizing influence will wane. Looking forward, into the deep future, the consequences of this lunar retreat are staggering. Millions of years from now, our days will continue to lengthen. The tides will grow weaker, their life-giving rhythm in the planet's intertidal zones fading to a mere whisper. The planet's axial tilt will become less stable, potentially leading to more extreme ice ages or periods of intense heat. And one of the most sublime and awe-inspiring celestial events visible from Earth will vanish forever. A total solar eclipse occurs because, by a stunning cosmic coincidence, the Moon is currently at the perfect distance to appear the exact same size in our sky as the Sun. This allows it to perfectly block the Sun's photosphere, revealing the ethereal, shimmering corona. But as the Moon moves further away, its apparent size in our sky is shrinking. Each year it covers a slightly smaller fraction of the Sun during an eclipse. In about 600 million years, the Moon will have receded so far that it will never again be large enough to completely cover the Sun. Future inhabitants of this planet will only ever see annular eclipses, where a ring of fire remains visible around the silhouetted Moon. The perfect sublime spectacle of totality will become a lost memory of a bygone astronomical age. The slow movement of our moon is erasing one of nature's greatest masterpieces from the future sky. This raises profound philosophical questions. We tend to view our world as a finished product, a stable stage upon which our human drama unfolds. But this is a fallacy. We live on a dynamic, evolving planet, in a solar system that is constantly, if slowly, changing. The moon's retreat is a stark reminder that nothing is permanent. The specific conditions that allowed for our existence are not a given. They are a fleeting arrangement in the grand sweep of cosmic time. We are living in a privileged moment, a sweet spot in the Earth-Moon relationship, and that moment is passing. The ominous 2024 prediction is more than just a warning about flooding. It is a profound lesson in interconnectedness. It shows how a distant, silent wobble in a celestial body's orbit can have tangible, devastating effects on our city streets. It demonstrates how a global phenomenon like climate change, driven by actions in one part of the world, can be amplified by gravitational forces and felt in another. It collapses the scale between the cosmic and the personal. The decision to burn fossil fuels is directly linked to the saltwater lapping at a shopkeeper's door, with the moon's orbital mechanics acting as the unforgiving mediator. So what can be done? We cannot stop the moon. We cannot halt its 18.6-year wobble, nor can we arrest its slow departure into the void. These are forces of nature, operating on a scale far beyond human control. The focus, therefore, must turn to the variable we can influence, the rate of sea level rise. The lunar cycle is a test, a deadline imposed upon us by the cosmos. It tells us that we do not have the luxury of endless debate or incremental action. The tide-amplifying phase of the 2030s will serve as a stark global report card on our efforts to combat climate change over the coming decade. If we fail to curb emissions, if we allow sea levels to continue their steep ascent, the consequences will not be delayed. The moon will ensure they arrive right on schedule. At the local level, coastal communities are in a race against time, a race against the tide. Engineers are designing massive seawalls, complex networks of pumps, and even elevating entire city districts. In places like the Netherlands, they have centuries of expertise in holding back the sea. But what they face is a new kind of challenge. Not just preventing storm surges, but managing the constant presence of water from below. These solutions are astronomically expensive and address the symptom, not the cause. They are a finger in a dike that is being stressed not only by rising waters, but by the rhythmic gravitational pulse of a wobbling moon. The movement of the moon, therefore, is more than a physical phenomenon. It is a movement in our awareness. It is forcing us to see our world not as a collection of isolated nations and ecosystems, but as a single, intricate system, where the melting of an Antarctic glacier is inseparable from the orbit of our satellite. It challenges our short-term thinking, demanding that we consider cycles that last not for an election term, but for nearly 2 decades. It asks us to look up at that familiar, comforting glow in the night sky and see it not just as an object of beauty, but as a gear in a vast planetary machine whose workings we are only just beginning to fully comprehend. For millennia, we have watched the moon, and it has watched us. It has seen empires rise and fall, continents drift, and our own species evolve from scattered tribes to a global civilization. It has remained a silent, passive observer, but now its passive dance is becoming an active intervention. Its subtle motions, amplified by our own actions, are sending a clear and urgent signal. The ground beneath our feet is not as solid as we thought. The shores we have built our greatest cities upon are not permanent boundaries. The rhythm of our world is changing. The moon is not moving to punish us. It is moving because of the fundamental laws of gravity and motion that govern the universe. It is our own alteration of the Earth's delicate energy balance that has turned this predictable cycle into an impending threat. The ominous prediction for the coming years is a reflection of ourselves. It is a mirror held up to our civilization, a mirror that orbits us every 28 days. When we look up at the moon now, we should feel not only a sense of wonder, but a profound sense of responsibility. Its silent silver face is now a clock, ticking down to a future of our own making, and the tides are rising. Look up into the silent, fathomless dark of a moonless night. Out there, suspended in the cold immensity, are points of light. Each one a sun, a distant star, a potential destination. For as long as we have been human, we have stared into that abyss. We have felt its pull, heard its silent, insistent call. It is a call to explore, to know, to venture beyond the familiar shore. It is the most profound and persistent dream of our species. The dream is not just of reaching these other worlds. It is the dream of how we will journey to them. In our collective imagination, the voyage is not a slow, patient crawl. It is a sudden, breathtaking leap across the cosmic ocean, a moment of impossible acceleration where the stars themselves warp. They do not simply drift past, they stretch into incandescent ribbons, luminous threads of light painting the windows of a vessel that travels not merely fast, but faster than everything. We have given this dream a name: warp speed. It is the promise of arriving at a world orbiting Alpha Centauri not in millennia, but in time for dinner. It is the fantasy of charting the spiral arms of our own galaxy within the span of a single human lifetime. A glorious vision of humanity, unbound, a species for whom distance has finally become a trivial thing, a conquered irrelevance. This is the future we have written for ourselves in story and film. A destiny where we are not just observers of the cosmos, but participants, citizens of a sprawling, interconnected galactic civilization. But in the universe we actually inhabit, the one governed by cold, unyielding mathematics. There is a law. It is not a suggestion nor a guideline open to interpretation. It is a fundamental statute woven into the fabric of reality itself, a cosmic edict that has governed every photon, every particle, every ripple of energy since the first instant of the Big Bang. This law is both beautifully simple and terrifyingly absolute. It states that there is an ultimate speed limit, a final frontier beyond which nothing, absolutely nothing, can travel. This cosmic speed limit is the velocity of light in a vacuum, 186,000 miles per second, nearly 300,000 kilometers every single second. A speed so ferocious it can circle our entire planet more than 7 times in the blink of an eye. It feels infinite, a velocity beyond all human comprehension. And yet in the arena of the cosmos, it is a warden, a gatekeeper that stands between us and our grandest ambitions. It is the universe's most profound and inescapable restriction. This documentary is the story of a monumental conflict, a clash between two titans of cosmic scale. In one corner, the boundless power of human imagination crystallized in the magnificent concept of warp speed, the dream of instantaneous travel of a universe made small. And in the other corner, the immutable, implacable reality of physics personified by the constant, unwavering speed of light, the supreme law that dictates the very rhythm of the cosmos. We will ask a question that cuts to the heart of our future. Which one of these titans truly wins? Is our dream of a warp-driven future a beautiful, noble fantasy destined to remain forever in the realm of fiction? Or is there a hidden path, a clever loophole in the laws of nature, a secret that could allow us to sidestep this ultimate barrier? The answer will take us on a journey to the very edge of science. We will explore the strange and bewildering world of Einstein's relativity, where time slows down and mass increases as you approach the limit. A realm where the universe itself actively conspires to prevent you from ever reaching its ultimate velocity. Imagine you are in a spacecraft, the most advanced ever built. You begin to accelerate, pushing your engines to their limits. As your speed increases, something strange begins to happen. From an outside perspective, your vessel's mass starts to climb. You are not adding any material yet, you are becoming heavier. The universe is resisting your acceleration with increasing force. It is like trying to run through water that becomes thicker, more viscous with every single step you take. The faster you try to go, the harder reality pushes back. You push the engines harder, pouring unimaginable energy into motion. 90% of light speed, 95, 99. The energy required for each new increment of speed skyrockets. Your mass approaches infinity. The energy needed to go faster becomes greater than all the energy contained in the known universe. You are running against a wall that grows infinitely solid the very moment you try to touch it. You can get infinitesimally close, but you can never break through. The speed of light is not a finish line you can cross. It is a horizon that you can only approach forever. This is the tyranny of the light speed limit, and to truly feel its crushing weight, we must confront the scale of the distances it so mercilessly governs. Let us take our fastest spacecraft, NASA's Parker Solar Probe. At its peak, it reaches a blistering 4,300,000 miles per hour, a stunning achievement of human engineering, our fastest creation. If we aimed that probe at our nearest stellar neighbor, Proxima Centauri, a mere 4.2 light-years away, the journey would take over 6,000 years. 6 millennia to cross the very first interstellar doorstep. The civilizations of ancient Egypt and Sumeria would rise and fall, the Roman Empire would be born and crumble to dust, all of history as we know it would unfold, and our tiny probe would still be voyaging through the lonely, silent darkness. This is the reality imposed by the universe's speed limit. It transforms the cosmos from a vast, explorable ocean into a collection of islands separated by uncrossable voids. It dictates that our star system is not a home but a cradle, and perhaps a prison from which we can never truly escape. But what if we could travel at the speed of light itself? Let us imagine a vessel that is pure energy, a ship of light. What would our journey look like then, traveling at the ultimate speed? The moon would flash past in little over a second. Mars, even at its closest, would be a journey of a few minutes. Jupiter, the king of our solar system, could be reached in half an hour. Our own celestial backyard would finally be within our grasp. This feels like freedom. This feels like victory. But this is where the illusion of mastery begins to shatter. Now let us point our ship of light toward Proxima Centauri. The journey, even at this impossible velocity, takes 4.2 years. A long time, but perhaps a manageable one for a dedicated crew. But what about the magnificent stellar nursery of the Orion Nebula? That beautiful glowing cloud where new stars are being born. Our beam of light, our vessel traveling at the cosmic maximum, would take 1,344 years to arrive. A message sent today would be received by a humanity so distant, so transformed by time, that they might be unrecognizable to us. Let us be bolder. Let us aim for the heart of our own galaxy, the supermassive black hole Sagittarius A star at the galactic core. That journey across our own cosmic city would take 26,000 years. A single human life becomes a meaningless fraction of the travel time. The very concept of a mission or a crew evaporates into absurdity. We are not explorers at that point. We are merely a message in a bottle adrift on an ocean of time so profound it defies our comprehension. And the journey to Andromeda, our closest galactic neighbor, 2.5 million years. 2.5 million years ago, our own ancestors were just beginning to master the use of primitive stone tools. The entire evolutionary story of Homo sapiens could play out from its genesis to its potential extinction, and our ship of light would still be hurtling through the intergalactic void, a silent testament to a species that dared to dream of crossing it. This is the chilling, sobering truth of the speed of light. It is not a gateway to the stars. It is the lock on the door. And so we are brought back to the great confrontation. The human imperative to explore, to expand, to become more crashes headlong into this fundamental cosmic barricade. It is the ultimate irresistible force meeting the ultimate immovable object. Is this then the end of the story? Are we destined to be a species forever? bound to a single star system, gazing out at a universe we can see and map and admire, but can never ever truly touch. Is our future one of glorious but permanent isolation? Perhaps not, because within the very physics that erects this wall there may be clues to its demolition. Science fiction, in its brilliance, imagined a way around the problem. It proposed that if you cannot travel through space faster than light, then perhaps you must find a way to make space itself do the traveling for you. This is the revolutionary idea at the heart of the warp drive. It is not a propulsion system in the traditional sense. It does not push a ship through the universe. Instead, it proposes to push the universe around the ship. Imagine the fabric of space-time as a vast flexible sheet. A warp drive would in theory be an engine that could bend this sheet. It would compress the fabric of space-time in front of the vessel, effectively shortening the distance to its destination. Simultaneously, it would expand space-time behind the vessel, pushing its starting point further and further away. The ship itself would remain stationary within this warp bubble. It would be like a surfer on a wave of space-time. The surfer isn't moving through the water, but the wave is carrying them forward. Crucially, inside this bubble of localized flat space-time, the ship would not be breaking any physical laws. It would not be traveling faster than light within its local frame. It would be at rest, floating in a small pocket of normal reality. But the bubble itself, this distortion in the cosmic fabric, could be propelled forward at speeds that mock the light barrier. 10 times the speed of light, 100 times, 1,000. Theoretically, there would be no limit. Andromeda could become a weekend trip. This is the audacious proposal of theoretical physics, a concept born not from a writer's pen but from the complex mind-bending mathematics of Einstein's own general theory of relativity. It is a tantalizing hint that the universe's rulebook might be more subtle, more wonderfully strange than we ever imagine. It suggests the cosmic speed limit is not an absolute prohibition on rapid interstellar travel, but a specific clause in a larger contract, a clause that might just contain an exit strategy, a loophole big enough to fly a starship through. But this loophole comes with an extraordinary price tag. To achieve this miraculous bending of space-time, the theory demands something that may not even exist. It requires a form of matter with properties so bizarre, so contrary to everything we know, that it has been dubbed exotic matter. It would need to have negative mass or generate negative energy density. It would have to possess a kind of anti-gravity, pushing space-time apart where normal matter pulls it together. We have never observed such a substance. We do not know if it is possible. This is the heart of our investigation. We will venture into the deepest, most speculative realms of modern physics. We will hunt for clues to the existence of this exotic matter, searching in the quantum foam and the echoes of the Big Bang. We will meet the scientists who are grappling with these colossal ideas, the intellectual heirs to Einstein who are pushing his theories into territories he never could have foreseen. They are the architects of humanity's most audacious dream. They are the ones asking if we can truly engineer the universe itself. So which is it to be? Are we to be forever humbled by the steadfast, unwavering glare of light speed, a cosmic law that keeps us in our place, a species of brilliant dreamers trapped on a lonely outpost in a vast, inaccessible cosmos? Or will our ingenuity, our relentless curiosity, our sheer refusal to accept limits unlock the secrets of warp speed? Will we become the masters of space-time, the voyagers we have always yearned to be, stepping out into a universe made new and accessible? The contest is set, the dream against the reality. The question is not just which one wins, the question is what it will mean for us when it does. There is a law governing your existence. It is more fundamental than gravity, more pervasive than time. It is a single number, a cosmic statute etched into the fabric of space-time itself, and it dictates the ultimate rhythm of reality. This law is not found in any human court or ancient text. It was divined from the strange behavior of light. It states that there is a speed you can never reach, a velocity that nothing with mass, not you, not a planet, not the fastest starship we can imagine, can ever attain. It is the universe's absolute unassailable speed limit, 300 million meters per second, the speed of light. It is known simply and elegantly as c. For most of human history, light was thought to be instantaneous, a divine switch thrown bathing the world in immediate brightness. But we learned to measure it to clock its finite pace, and we found it to be staggeringly fast yet undeniably finite. The true revolution, however, came not from a telescope, but from the mind of a single man. In 1905, a young patent clerk in Bern, Switzerland, named Albert Einstein, was wrestling with a profound contradiction, a paradox hidden within the elegant mathematics of light and magnetism. The equations suggested something absurd, something that defied all common sense and the revered physics of Isaac Newton. They suggested that the speed of light was constant. Not just constant in a vacuum, constant for everyone. It didn't matter if you were standing still. It didn't matter if you were flying towards a light beam in the fastest rocket conceivable. It didn't even matter if you were speeding away from it. You would always measure that beam moving at the exact same speed. Imagine you are on a cosmic highway. A car passes you at 60 miles per hour. If you speed up to 50, it now seems to pass you at only 10. Simple, intuitive. This is the world as we know it. But light breaks this rule. It shatters our intuition completely. If a beam of light passes you, a cosmic bullet of pure energy, you will clock it at the speed c. Now you ignite your engines and chase it at half the speed of light. Logic dictates you should now measure its speed as only half of c, but you don't. You measure it impossibly as the full speed c. You push your ship to 99% of light speed, and still that beam pulls away from you at the exact same velocity, the speed of light. This is the bedrock of our modern understanding of the universe, a puzzle that seems to defy all logic. How can a speed be absolute regardless of the observer's motion? Einstein realized that for this to be true, something else, something we thought was rigid and universal, had to give. The very foundations of reality had to be flexible, space and time itself. To preserve the constancy of light, the universe plays a trick. It forges a strange and powerful new relationship between how you move through space and how you move through time. They are not separate. They are two threads in a single fabric space-time. And the faster you travel through space, the slower you are compelled to journey through time. This isn't science fiction. It is a fundamental consequence of c. It is called time dilation. It means that a clock in motion ticks slower than a stationary one, not because of a mechanical flaw, but because time itself is flowing at a different rate for that moving object. Every atomic vibration, every chemical reaction, every thought is literally proceeding at a more leisurely pace. We see this every day, though the effect is imperceptibly small. GPS satellites orbiting high above Earth are moving incredibly fast. Their internal clocks tick just a little bit slower than our clocks down here on the ground. If our engineers didn't account for this relativistic effect, this subtle warping of time, your GPS would become useless in a matter of hours, sending you miles off course. The implications when scaled up are profound and deeply unsettling. Imagine a journey to our nearest stellar neighbor, Proxima Centauri. It lies just over 4 light-years away. Let's imagine a starship, a marvel of future engineering that could travel at 90% of the speed of light. From the perspective of mission control on Earth, the journey would take about 4.5 years. But for the astronauts on board, that ship time would flow differently. Their clocks, their aging, their perception of moments passing would be compressed by their incredible velocity. For them, the journey would last only 2 years. They would arrive at their destination younger than they should be, having experienced less time than their loved ones back home. This isn't a trick of perception. It is a physical reality. They have traveled through space at a tremendous velocity, and the universe has exacted a payment in the currency of time. Now let's amplify this effect. Let's push our hypothetical ship to 99.99% of light speed. A voyage to the center of our Milky Way galaxy, some 26,000 light-years from Earth. For the anxious observers on our home world, the journey is an eternity. A signal confirming the ship's arrival wouldn't reach us for 26,000 years. Civilizations would rise and fall. The very coastlines of our continents would shift and change. Humanity might transform into something unrecognizable or disappear entirely. The travelers would be a myth, a legend from a forgotten past. But for the crew cocooned in their relativistic vessel, the story is astonishingly different. Their passage through time has slowed to a crawl. The immense gulf of 26,000 light-years would be crossed in what feels to them like a mere 367 years. Still a multi-generational journey, but not the geological timescale experienced by the universe they left behind. They could, in theory, complete the round trip in just over 700 years of their own personal time. But upon their return to Earth, they would not find their families. They would not find their nations or their cultures. They would arrive back 52,000 years in the future. They would be strangers on their own planet, relics of a history so ancient it has faded into dust. This is the famous twin paradox, and it is no paradox at all. It is the stark, beautiful, and terrifying logic of Einstein's universe. The speed of light doesn't just warp time, it erects an even more formidable and absolute barrier. It governs the relationship between energy and matter itself. This is the truth captured in the most famous equation ever written, E equals mc squared. Energy equals mass times the speed of light squared. This equation is a cosmic ledger. It tells us that mass is a fantastically concentrated form of energy, and that energy, in turn, has a kind of mass. It's not a metaphor. When you run, your kinetic energy actually adds a minuscule amount of mass to your body. When you heat a cup of coffee, it becomes infinitesimally heavier than when it was cold because you have added energy to it. At everyday speeds, this effect is completely negligible. But as you approach the speed of light, it becomes everything. Imagine you are piloting our starship once again. You fire your engines, converting fuel into kinetic energy. Your ship accelerates. It gets faster and faster. But a strange thing begins to happen. As your velocity increases, so does your ship's effective mass. Your engines, which once gave you a powerful push, now seem less effective. Each new burst of thrust yields a smaller and smaller increase in speed. It's like trying to push a boulder that gets heavier with every single step you take. At 90% of light speed, your ship's mass has more than doubled. Your engines must now work twice as hard just to gain a little more speed. You push the throttle to its absolute limit. You are now at 99.9% of the speed of light. Your vessel, once a sleek explorer, now behaves as if it has the mass of a mountain. It resists any further acceleration with a staggering, almost infinite inertia. The energy you pour into your engines is no longer making you significantly faster. Instead, it is being converted directly into mass. And there, shimmering just ahead of you, is the finish line, the absolute speed of c. To reach it, to close that final infinitesimal gap, your mass would have to become infinite. And to accelerate an infinite mass, you would need an infinite amount of energy, more energy than exists in the entire observable universe. This is not a technological problem to be solved. It is not a matter of building better engines or finding more exotic fuel. It is a fundamental law of the cosmos. The speed of light is a horizon you can approach forever, but a boundary you can never ever cross. It is the ultimate insurmountable wall built into reality's architecture. For anything with mass, the universe has a clear rule: look but do not touch. So we have this supreme cosmic law, this elegant principle that both warps time and forges an infinite energy barrier. What does this truly mean for us, for a species that looks to the stars with a burning ambition to explore? It means the universe in its staggering immensity is also a prison, a magnificent, beautiful and inescapable cage. Let us recalibrate our sense of scale. We speak of light years with a casual familiarity, but the term masks a distance that is profoundly alienating. 1 light year is the distance light travels in a single year. That is nearly 6 trillion miles. Almost 10 trillion kilometers. A number so large it's practically meaningless to the human mind. Our closest star system, the Alpha Centauri trio, is just over 4 light years away. If we could travel at the speed of light, which we have established is physically impossible for a spacecraft, it would still take more than 4 years to get there, one way. And that is our very next-door neighbor. The Voyager 1 probe is the fastest object humanity has ever sent hurtling into interstellar space. It travels at an astonishing 38,000 miles per hour. At that velocity, if it were pointed toward Proxima Centauri, the journey would take over 75,000 years, 75 millennia to cross the gap to the very first star beyond our own sun. Our galaxy, the Milky Way, is a sprawling spiral city of stars. It contains perhaps 400 billion suns, and it is 100,000 light years across. To traverse it, even at the impossible speed of light, would require 100,000 years. Human civilization, from the first cave paintings to the digital age, has existed for less than half that time. We send radio signals out into the cosmos hoping for a reply. Imagine a civilization exists 50,000 light years away near the galactic core. Our message, traveling at light speed, takes 50 millennia to arrive. If they were to receive it today and reply immediately, their answer would not reach Earth for another 50,000 years. The entire conversation would span a period of time longer than the history of our species. This is the profound isolation imposed by C. The stars we see in the night sky are not as they are, but as they were. We are looking at ghosts of light. The light from Rigel in the constellation of Orion began its journey 860 years ago. When that light left its star, Earth was deep in the Middle Ages. We see the star Betelgeuse as it was 640 years in the past. For all we know, it may have already exploded in a supernova. The news of its death, traveling at the ultimate cosmic speed, is still on its way. We are living on an island, a beautiful, life-giving island we call the solar system, but it is surrounded by an ocean of distance so vast that the law of light speed forbids us from ever crossing it in any meaningful human timescale. Every star is another island locked in its own quarantine of spacetime. We can receive postcards of ancient light, but we can never visit. We can never truly know our neighbors. The Milky Way becomes a gilded cage, its spiraling arms filled with untold wonders, nebulae and new worlds are the ornate bars of our confinement. The universal constant that holds atoms together and allows stars to shine is the very same constant that chains us to our lonely corner of space. We have discovered the supreme rule of the universe, only to find that it is a judgment of solitary confinement. This is the grand and frustrating irony of our cosmic awareness. Our minds, through the power of science and imagination, can leap across galaxies in an instant. We can simulate the birth of the universe and the death of stars. We can conceive of interstellar empires and galactic federations. Our ambition is boundless, our curiosity unquenchable, but our physical bodies are bound by a physical law that is absolute. Humanity has always been a species of pioneers, of explorers. We crossed continents, we sailed oceans, we climbed mountains, we even left our world and set foot upon the moon. It is in our very nature to push against boundaries to see what lies beyond the next horizon. But here we have found a horizon that is not made of rock or water. It is a horizon woven from the very nature of space and time. So we are faced with a monumental choice. Do we accept this limitation? Do we resign ourselves to being a species forever tethered to a single star, destined to live and die in this one system, while a universe of infinite possibility glitters tantalizingly, forever out of reach? Or do we dare to dream of something more? Do we dare to ask a question that borders on scientific heresy? What if there is a way to cheat? What if the unbreakable law isn't the only law in town? The speed of light may be the fastest you can travel through space. But what if the solution is not to travel through space at all? What if instead you could find a way to bend, to fold, to warp the very fabric of space-time itself? This is the seed of rebellion against the tyranny of C. It is the genesis of a dream called warp speed. What if the ultimate secret to crossing the unimaginable voids between the stars is not to move at all? What if the grand cosmic speed limit, the sacred law of light, could be sidestepped, not by breaking it, but by ignoring it entirely? This is not a riddle. It is a profound proposition born in the realm of science fiction that has found a startling echo in the deepest mathematics of our universe. For decades, we saw it as pure fantasy, a convenient plot device to propel starship captains from one adventure to the next in the span of a television episode. The command was iconic, a promise of boundless exploration, warp speed. It was a daydream, a collective wish for a future where humanity was not marooned in its own solar system, a prisoner of distance. But then in 1994, a theoretical physicist named Miguel Alcubierre decided to treat the daydream with the seriousness of a scientific query. He asked a simple yet revolutionary question. Could the equations of Albert Einstein, the very architecture of reality, actually permit such a thing to exist? The answer he found would forever blur the line between fiction and possibility. To understand the warp drive, you must first forget everything you think you know about propulsion. Forget rockets pushing against a plume of fire. Forget ion engines gently accelerating over months and years. The Alcubierre drive is something else entirely. It is not an engine that moves a ship through space. It is an engine that moves space itself, carrying the ship along for the ride. Imagine you are standing on a long plush carpet. Your destination is at the far end, hundreds of feet away. You could walk step by step a long and tedious journey. But what if instead you could grab the carpet in front of you and pull it towards you, creating a wrinkle? The destination comes to you, and you haven't taken a single step. This is the foundational principle of the warp drive. The ship nestled inside a protective bubble remains perfectly still. It experiences no acceleration, no crushing G-forces, no sense of motion. It is, for all intents and purposes, a tranquil island of calm. But outside this bubble, reality itself is being violently re-engineered. The device would generate a wave of space-time. In front of the vessel, the fabric of the universe would be compressed, squeezed together like an accordion. The distance to the destination is dramatically artificially shortened. Simultaneously, behind the vessel's space-time would be fantastically expanded, unfurling and stretching out at an accelerated rate. The point of origin is effectively flung away into the cosmic rearview mirror. The ship is not flying, it is surfing. It is riding a ripple of its own making on the ocean of space-time. From the perspective of an outside observer, the ship would appear to vanish from one point and reappear at another, seemingly traveling faster than a beam of light. But here is the sublime, rule-bending genius of the concept. The ship itself never violates the local speed of light. Within its little pocket of space-time, it is not moving at all. The bubble, this distortion in the cosmic geometry, is what travels. And, according to Einstein's theories, there is no known limit to how fast a distortion in space-time can propagate. You are on a cosmic escalator standing still while the universe itself glides past you at an impossible velocity. This idea, as outlandish as it sounds, is not forbidden by our best understanding of the cosmos. In fact, it is born from it. It is a direct consequence of the single greatest revolution in our perception of reality, Albert Einstein's general theory of relativity. Before Einstein, we imagined space as a static, empty stage, a rigid, unchanging grid upon which the drama of the universe played out. Objects moved through this arena, but the arena itself was fixed. Einstein shattered that perception forever. He revealed that space and time are not separate, but are woven together into a single dynamic four-dimensional fabric, space-time. And this fabric is not rigid, it is active, it is malleable. It can be bent, stretched, twisted, and warped. What causes it to warp? Mass and energy. As the physicist John Wheeler elegantly summarized it, space-time tells matter how to move, matter tells space-time how to curve. Every star, every planet, every speck of dust creates a depression, a curvature in this cosmic fabric. A planet orbiting a star is not being pulled by a mysterious invisible rope. It is simply following the straightest possible path through a curved space, rolling along the contours of a gravitational well created by the star's mass. We see this happening everywhere we look. Gravity is not a force in the old sense. It is the geometry of the universe. We have even witnessed the most extreme predictions of this theory. Gravitational waves, ripples in space-time itself, unleashed by the cataclysmic collision of black holes, have been detected here on Earth billions of years after their creation. These waves are space-time itself, stretching and squeezing, propagating across the cosmos at the speed of light. So we know for a fact that space-time is not a passive backdrop. It is an active participant in the cosmic dance. It can be manipulated. This is the crucial scientific permission slip for the warp drive. If space-time can be warped by stars and black holes, then the question becomes, could we learn to warp it ourselves? Could we become architects of our own local geometry? This is the territory Miguel Alcubierre ventured into. He wasn't performing an experiment in a lab. He was exploring the possibilities hidden within Einstein's own mathematics. His 1994 paper laid out the precise mathematical recipe, the specific geometric configuration required to create this warp bubble. It was a formal blueprint. It described a metric, a mathematical tool for measuring distances in a curved space-time that had all the properties of a warp drive. A flat, undisturbed region on the inside, perfect for a spacecraft and its crew, surrounded by a shell of the most extreme space-time curvature imaginable. The math worked. It was consistent. It did not break any known laws of physics. For a moment, the stars seemed closer than they had ever been. The dream of interstellar travel had found its first tentative footing in the rigorous language of theoretical physics. Imagine what it would be like to be a passenger aboard such a vessel. The journey begins not with a roar, but with a silent reshaping of the world. Through the forward viewports, the constellation of Orion, light years distant, might suddenly appear vast and close its stars, no longer pinpricks but brilliant disks. The space between you and your destination has been folded. Behind you, the familiar light of our own sun would be stretched, redshifted into a dim infrared memory. The space you just occupied is being inflated like a colossal balloon, and yet inside your cabin your coffee remains perfectly still in its cup. You feel no sense of speed, no violent lurch of acceleration. You are in the eye of the hurricane, a zone of absolute placidity while the universe itself churns and contorts around you. Your clocks would tick at their normal rate. Your biology would be unaffected. You could walk from one end of the ship to the other, and your local physics would be entirely mundane. The journey to Alpha Centauri, a 4-year trip for light itself, might be completed in a matter of weeks or days or even hours, depending on the intensity of the warp field you could generate. You would arrive not as a weary traveler aged by a long voyage, but as someone who simply stepped from one room into another. The destination would resolve back into its normal geometry as the drive powers down. The carpet of space-time flattens out. You would have crossed an interstellar chasm without ever really moving. You cheated cosmic law. You found a loophole in the tyranny of light speed. It is perhaps the most elegant and profound vision for interstellar travel ever conceived. A testament to the power of pure mathematics to illuminate paths our technology has yet to tread. It seems too good to be true. A perfect solution, and for now it is, because Einstein's equations, while permitting the geometry of a warp drive, also demand a price tag. A price so steep, so far beyond our current understanding of reality that it relegates this beautiful concept back to the very edge of science. The blueprint comes with an impossible list of materials. To create the warp bubble to bend space-time to your will, you need more than just energy. You need a very specific and very strange kind of energy. To create the expansion of space-time behind the ship, you need something that acts like anti-gravity. You need something that pushes the universe apart. The equations are unambiguous. They demand the existence of what physicists call negative energy density, or more colloquially exotic matter. This is the heart of the problem, the great towering barrier that separates the warp drive from reality. We live in a universe dominated by positive energy and positive mass. Matter as we know it is positive. It has a gravitational pull. It attracts other matter. It creates the familiar gentle curves of space-time that form galaxies, stars, and planets. Energy from the light of a star to the heat in a chemical reaction is positive. It contributes to the mass energy of the universe and therefore to gravity. Every single thing you have ever touched, seen, or interacted with is made of this positive stuff. It is the bedrock of our physical existence. Negative energy is its theoretical opposite, a cosmic ghost. If positive mass is a bowling ball placed on a trampoline, creating a dip, negative mass would be like an anti-bowling ball. It would create a hill, a peak, a region of anti-gravity. It would repel everything around it. It is this repulsive anti-gravitational property that is required to generate the expanding space-time behind the Alcubierre drive. This is the push that flings the origin point into the distance. The concept sounds utterly bizarre, like something from a fantasy novel. What would it even be like? A lump of negative matter would not fall down. It would fall up. If you pushed it, it would accelerate towards you, not away from you. It violates our deepest intuitions about how the world is supposed to work. And here is the most critical point. In the entire history of science, we have never once held, measured, or definitively observed a single ounce of this material. It has never appeared in any particle accelerator. It has never been detected by any telescope. It exists for now only as a phantom in our equations, a mathematical necessity for a desired outcome. Physicists have flirted with concepts that produce similar effects. The Casimir effect, for example, is a real measured phenomenon where the quantum vacuum between two closely spaced plates can exhibit a net negative energy density compared to the vacuum outside. It's a tantalizing hint, a whisper from the quantum world that negative energy states might be possible, but the amounts are infinitesimal, microscopic, fleeting. They are a universe away from the stable, controllable, and vast quantities of negative energy needed to envelop a starship. The early calculations for Alcubierre's drive were staggering. Some suggested you would need a ball of negative energy with the mass of the planet Jupiter to create a stable warp bubble. Later, refinements brought the numbers down, but the requirements remain in the realm of planetary or stellar-scale engineering. We are not talking about building a new type of engine. We are talking about needing to manufacture a substance whose existence is not even confirmed on a scale that dwarfs all of human civilization's combined energy output. It's like discovering a blueprint for a magical castle, only to find the sole building material is solidified moonlight. The blueprint is beautiful, the math is sound, but the foundational ingredient is pure conjecture. This single requirement has ignited one of the most fascinating and contentious debates in theoretical physics. Is negative energy truly impossible, a sign that the laws of physics have a hidden clause forbidding such creations, or is it simply a form of matter energy, so strange, so alien that we have not yet developed the science to even recognize it? Some physicists argue that nature must have a chronology protection conjecture, a fundamental principle that prevents the creation of exotic phenomena like warp drives or time machines that could violate causality. Negative energy, they believe, is the key that must remain lost, lest we unlock paradoxes that would unravel the fabric of reality. The creation of a warp bubble could, in theory, lead to scenarios where you could arrive at your destination before you even left. The consequences for the cause and effect nature of the universe are profound. Others are more optimistic. They suggest that our understanding of quantum gravity, the yet-to-be-discovered theory that will unite Einstein's relativity with the bizarre world of quantum mechanics, might reveal new forms of matter and energy. Perhaps in the churning quantum foam that underpins reality, or in the heart of a black hole, or in the echoes of the Big Bang, the secrets to creating and controlling negative energy are waiting. It would require a revolution in physics as profound as any that has come before. We would have to move beyond just understanding the universe and learn to write new sentences with its fundamental grammar. So the warp drive stands today as a magnificent paradox. It is a mathematically sound solution to an unsolvable problem. It is a plausible impossibility. It adheres perfectly to the known laws of general relativity, while simultaneously demanding an ingredient that seems forbidden by every other observation we have ever made. It is the ultimate expression of humanity's desire to reach the stars, and the ultimate reminder of the colossal obstacles that lie in our path. The question is no longer just can we build it, the question is does the universe even contain the right parts? The answer lies somewhere out there in the unexplored territory where our theories break down and true discovery begins. A tantalizing dream suspended between the known and the unknowable. For a century it was the final word. The universe had a speed limit, and nothing could break it. The velocity of light in a vacuum, a perfect, inviolable constant. It was the foundational wall of Einstein's physics, a barrier that confined humanity to its cosmic cradle. To travel to the stars meant to surrender to generations of time, a journey into the void where only light could truly race. Science fiction dreamed of a way around this ultimate restriction, a cheat code for the cosmos called a warp drive, but it remained firmly in the realm of fantasy, an entertaining fiction for the screen and the page, until a young physicist in Wales looked at the wall and saw not a barrier but a door. His name was Miguel Alcubierre, and in 1994 he did something quietly revolutionary. He stopped treating faster than light travel as a fantasy. He began treating it as a problem of general relativity. He wasn't trying to break the cosmic speed limit. He was looking for a loophole within the laws themselves. What if, he wondered, you didn't have to move through space? What if instead you could make space itself move for you? The question was audacious, almost an act of theoretical heresy. It challenged the very bedrock of our understanding of motion. And from that question, an equation was born, a piece of mathematics now known as the Alcubierre metric. It's a blueprint for the impossible, a recipe written in the language of space-time geometry. It describes a method for scrunching up the universe. Imagine you are standing on a vast, infinitely stretchable rug. The distant stars are patterns on the far side of that rug. To reach them, you don't have to run across the fabric. Instead, you could have the rug pulled towards you from the front, while the section of rug behind you is stretched out. You standing in the middle haven't actually moved at all. You have remained perfectly still on your little patch of carpet, and yet you have traversed an enormous distance, almost instantly. This is the sublime, bewildering genius of the Alcubierre drive. It proposes not a starship but a bubble of spacetime, a localized, self-contained warp in the cosmic fabric. Inside this bubble, your vessel is an island of perfect calm. You would feel no acceleration, no crushing G-forces. You would float weightless as if parked in orbit around Earth. Because according to the local physics inside the bubble, you are not moving faster than light. You aren't even moving. You have broken no laws. The cosmic speed limit remains intact. It is the bubble itself, the disturbance in spacetime, that travels. This disturbance is an elegant, violent cosmic wave. In front of the bubble, spacetime is intensely compressed. Vast distances are squeezed into impossibly thin layers. Behind the bubble, spacetime is dramatically expanded. It is stretched and pulled, creating new distance where none existed. Think of it as a surfer on a wave of pure geometry. The surfer doesn't propel themselves through the water. They are carried forward by the motion of the wave itself. The Alcubierre drive is a starship that surfs the universe. It creates its own wave, a ripple of space-time under its command. And because it is space itself that is contracting and expanding, the bubble's potential velocity is in theory limitless. It is not bound by the speed of light. It could cross a galaxy in what feels like an instant. It could connect worlds separated by unimaginable gulfs of darkness. It could make the entire observable universe our neighborhood. This was the breathtaking proposition Alcubierre put on the table, not with fanciful stories, but with the cold, hard rigor of mathematics. When he published his paper, the physics community was stunned. It was a solution to Einstein's field equations. This wasn't a guess. It wasn't a philosophical concept. It was a mathematically consistent, valid piece of theoretical physics. The very framework that established the light-speed barrier, general relativity, also contained the seeds of its own subversion. It was as if Einstein, in locking the door, had accidentally left the key sitting right on the mat. For the first time, a warp drive was no longer just a fiction. It was a theoretical possibility, a ghost haunting the equations, a whisper from the cosmos that our destiny might not be confinement, but the universe gives up its secrets at a tremendous price, and the price for this miracle was stranger than anyone could imagine. The mathematics held, the equations were sound, but they came with a shopping list from another reality. To create this specific miraculous distortion of space-time, to generate the expansion needed behind the bubble, you would need something that shouldn't exist. Something physicists call exotic matter, something with properties that defy all common sense. To understand what this means, think about normal matter. The planets, the stars, you and I, we all have positive mass. And positive mass generates gravity, an attractive force. It pulls things together. It curves space-time inward, creating valleys. A planet sits in space-time like a bowling ball on a trampoline. It creates a dimple. Other objects roll down into that dimple. This is gravity. Predictable, familiar, constructive. Now imagine something entirely different. Imagine a substance with negative mass. If you were to push it, it would accelerate towards you, not away. Its inertia is backward. It resists force in the wrong direction, and its effect on space-time would be the exact opposite of gravity. Instead of a bowling ball on a trampoline, it would be a helium balloon pushing up from underneath the fabric. It would create not a valley but a hill, a region of anti-gravity, a repulsive force. It would cause spacetime to curve outward to expand. This is the fundamental ingredient for the Alcubierre drive. This is the engine of expansion, the exotic fuel required to stretch the universe. To build a warp bubble, you would need to craft a shell, a delicate, impossibly dense shell of this negative mass matter. This shell would generate the powerful anti-gravitational field. It would push space-time apart behind the ship, creating the wave. The very idea is a vertigo-inducing plunge into the unknown, matter that weighs less than nothing, energy that pushes the universe apart instead of pulling it together. Is such a thing even real, or is it just a phantom of the math? For decades it seemed like a pure fantasy, a deal-breaker that relegated the warp drive back to fiction. But the cosmos is always more clever, more subtle than we think. It turns out we have seen hints of this strangeness before. In the strange world of quantum mechanics, a place of ghosts and probabilities, we find something called the Casimir effect. Imagine two perfectly flat, uncharged metal plates, placed fractions of a millimeter apart in a perfect vacuum. Our intuition tells us nothing should happen. There is no force between them, but our intuition is wrong. The plates are pushed together by an unseen, mysterious energy. This force comes from the vacuum itself. The quantum vacuum is not empty. It is a roiling sea of potential, a chaos of virtual particles popping into and out of existence. When you place the two plates close together, they restrict which of these virtual particles can appear between them. More particles can appear outside the plates than inside. This imbalance creates a pressure that pushes the plates together from the outside. But here is the crucial insight. The region between the plates now has less energy than the empty vacuum surrounding it. It is a pocket of space with a negative energy density. It is real. It is measurable. We have created it in our laboratories. It is a tiny, fleeting, almost infinitesimal fragment of the very exotic energy the Alcubierre drive requires, so the universe allows it. The laws of physics permit its existence. The fundamental show-stopping ingredient is not impossible after all. A wave of excitement rippled through the theoretical community. The door that seemed permanently locked had just cracked open a sliver. The phantom of the math had shown its face in the real world. But this tiny glimmer of hope was almost immediately eclipsed by a shadow of truly gargantuan proportions. The problem wasn't just what kind of fuel you needed. It was the staggering, mind-shattering quantity the equations demanded. Alcubierre's original calculations were terrifying. To create a stable warp bubble, large enough for a small starship, and propel it at 10 times the speed of light, you would need an amount of negative energy equivalent to the mass of the entire observable universe. It was a solution that required you to consume reality itself. The dream seemed to die right there, a mathematically beautiful but physically absurd proposition, a formula for a godlike power that no civilization could ever wield. But science is not a single declaration. It is a conversation, a process of refinement, of challenging, of pushing the numbers. Other physicists took up Alcubierre's work. They began to play with the geometry of the warp bubble. What if you didn't make the bubble a perfect sphere? What if you changed the thickness of its walls? What if you shaped it more like a donut, a torus? A physicist at NASA, Harold Sonny White, led this new charge. His team tweaked the equations, searching for a way to reduce the catastrophic energy requirements. And they found one. By oscillating the warp bubble by creating a pulsating wave, they discovered the energy demands could be dramatically lowered. The numbers began to fall, from the mass of the universe down to the mass of a galaxy. Still impossible, but a step in the right direction. Further refinements brought it down to the mass of a large star. Then, with more exotic geometries, a shape like a flattened ring, the requirement plummeted to the mass of a planet like Jupiter. Then, finally, to the mass of a spacecraft like Voyager. From a universe to a planet to a probe, this was a monumental leap in theoretical feasibility. The numbers were still immense, far beyond any technology we possess. But they had moved from the realm of the physically impossible to the realm of the merely colossally difficult. This is a critical distinction in the world of theoretical physics. It marked a transition from a beautiful mathematical artifact to a potential, albeit distant, engineering problem. We were no longer talking about consuming galaxies. We were talking about converting a large object's mass into negative energy. The challenge was still godlike, but it was no longer a logical absurdity. The path from our world to the stars was not paved with impossible math. It was paved with monumental but perhaps not insurmountable obstacles, and the energy requirement was only the first in a new line of paradoxes. Let us assume for a moment that we solve the energy crisis. Imagine a future where we can generate Jupiter's worth of negative energy. We have the fuel. We are ready to build the engine. But what happens when we turn it on? This is where the next set of bewildering challenges emerge. The first is the problem of stability. The warp bubble is a structure of unimaginable energy density, a construct woven from the most extreme physics in the universe. It is balanced on a mathematical knife's edge. The slightest fluctuation, a single stray particle, could potentially cause the entire bubble to become unstable. What happens then? Some models suggest it would simply evaporate, fizzling into nothing, a disappointing but harmless end to the journey. Other more frightening calculations suggest a far more violent fate. The immense energies involved could cause the bubble to collapse. It might create an event horizon, the point of no return for a black hole. Your starship, your crew, your historic mission, all instantly annihilated, crushed into a singularity. Or perhaps it would unleash a wave of high-energy radiation, a gamma-ray burst that would sterilize everything in its path. We simply do not know. The physics is so extreme, so far beyond our experimental reach, that our theories can only offer educated and often contradictory guesses. To build a warp drive is to tame a cosmic hurricane, to ride a storm of pure spacetime and pray it does not turn on you. Even if we could guarantee a stable bubble, an even stranger problem appears, a paradox of control that seems to defy the very nature of causality. Think about the pilot inside the starship. They are nestled in their pocket of flat, calm space-time. They are causally disconnected from the outside universe. No signals, no light, no information can cross the bubble's boundary from the outside to the inside. This protects them from the hostile environment of warped space, but it also creates a profound and terrifying dilemma. The front of the bubble, the very region of space-time being compressed, is moving faster than any signal the pilot could send to it. It is by definition traveling at superluminal speeds. This means the pilot inside the bubble cannot see what lies ahead. They cannot send a command to the front of the bubble to turn. They cannot tell it to slow down or to stop. Once the journey begins, the ship is blind. Its path is predetermined at the moment of its creation. You would have to plot your entire course with impossible precision before you even left port. You would have to account for every stray asteroid, every dust cloud, every gravitational wobble across light years of space, because once you push the button, you are no longer a pilot. You are a passenger in a cannonball of reality, a message in a bottle thrown across the cosmic ocean with no ability to steer around the rocks that lie in wait. You are racing towards a destination you can neither see nor change. How do you even create the bubble in the first place? To initiate the warp, you need to assemble the shell of exotic matter. But to assemble it, parts of that shell must travel faster than light to get into position around the stationary ship. It's a classic chicken and egg problem. You need a warp drive to build a warp drive. It's a paradox that suggests such a structure can't be made from scratch. Perhaps it has to exist naturally or be created by other unknown means. And what of the arrival? The immense energy required to compress spacetime in the front doesn't just vanish. Theoretical models show that it would accumulate during the journey. Particles from the interstellar medium swept up and supercharged. Upon arrival at your destination, when the drive is turned off, this accumulated energy would be released in a devastating blast. A flood of high-energy particles potentially powerful enough to obliterate anything and everything at your destination. You could reach another star system in a week. But your arrival might announce itself with the force of a supernova. Not the triumphant landing of explorers, but the silent, deadly impact of an extinction-level event. You could travel to the stars, but you could never safely visit them. So this is where the dream now stands, torn between mathematical elegance and physical nightmare. The door that Alcubierre opened leads into a labyrinth, a maze of colossal energy, requirements of terrifying instabilities, of paradoxes in control and catastrophic consequences. Each solution seems to give birth to a dozen new, more difficult problems. The science has moved forward, taking the idea seriously, but the mountain we must climb to achieve it has grown ever taller. It is no longer a simple wall, it is an entire range of forbidding peaks, each one higher than the last. Reaching for the stars, it seems, is not just a matter of speed. It is a matter of commanding the very essence of reality, of rewriting the rules of space and time at a fundamental level. The question is no longer, can it be done in theory? The question is, could any civilization, no matter how advanced, ever truly hope to master such forces? Or are some dreams by their very nature destined to remain as beautiful, tantalizing, and unreachable as the stars themselves, have chased a ghost through the equations, a spectre of impossible speed, a dream of starships slipping between the folds of spacetime itself? We have imagined a future where the gulfs between suns are not barriers but merely passages, where humanity is not confined to this solitary cradle but is a citizen of the galactic community. This is the sublime promise of the warp drive. But now our journey takes a darker turn. We must descend from the pinnacle of imagination into the cold, unforgiving abyss of physical law. For it is here in the fine print of the cosmos that we discover the dream of warp speed is not just difficult, it might be a fundamental impossibility, a door to which the universe has deliberately lost the key. The path to the stars we are about to find is guarded by dragons of unimaginable power. Our first confrontation is with a substance so strange, so contrary to every piece of matter we have ever touched, that it has earned the name exotic. To build a warp drive, to bend space to your will, you cannot simply push it with conventional energy. That would be like trying to lift yourself by your own bootstraps. You need something that can create anti-gravity. You need to generate a region of repulsive spacetime. This requires a form of matter or energy with a negative density. Imagine all of reality as a vast torch sheet. A planet, a star, your own body. Each one is a weight creating a depression, a gravity well in that sheet. Everything we know does this. It is the definition of mass. But the warp drive demands the opposite. It needs something that pushes the sheet upward, a source of cosmic buoyancy, a phantom presence that makes spacetime curve away from it. This is what physicists call exotic matter. It is a ghost in the universal machine, a whisper in the equations that has never materialized, into a single observable particle in any experiment. It is the cornerstone of our starship, and it does not exist, or at least we have never found it. The search has driven us to the quantum realm, the flickering, uncertain basement of reality. Here in the microscopic vacuum between two parallel plates, a phenomenon known as the Casimir effect appears. Quantum fluctuations in the void create a subtle pressure, a tiny region where the energy density is slightly less than the surrounding vacuum, technically negative. For a moment it seemed like a breakthrough, a microscopic proof of concept, a crack in the door, but the hope was fleeting, a mirage in the quantum foam. The negative energy from the Casimir effect is minuscule, ephemeral, and locked into a specific geometry. It offers no path to creating a stable macroscopic field powerful enough to envelop a starship. It is like finding a single damp splinter of wood and proclaiming you can now build an ark to sail the heavens. The sheer quantity of this negative energy field required is beyond staggering. Its stability is a complete unknown. And what would this material even be like? If you could hold a piece of it in your hand, what would it do? The predictions are bewildering. According to the mathematics, it would have negative mass. If you pushed it, it would accelerate towards you. It would violate Newton's most basic laws of motion. It would fall upward in a gravitational field, fleeing from the very planets and stars that define our cosmos. It possesses properties so paradoxical, so alien to the fabric of our universe, that its existence might be forbidden by a deeper, still unknown principle, a cosmic censor that prevents such absurdities from forming. So the first and perhaps greatest barrier stands before us. The engine of our dreams requires a fuel that may be a physical contradiction. We are asked to build our cathedral to the stars with bricks that crumble into nothingness upon inspection. This is not an engineering challenge to be solved with cleverness. This is a fundamental crisis. The universe itself appears to be telling us no. But let us for a moment indulge in a fantasy. Let us imagine that a deposit of this impossible material is discovered, or that a genius yet unborn finds a way to manufacture it. The first dragon is slain, but a second, far larger, now awakens. This beast is not made of exotic physics, but of raw brute force. It is the monster of energy, the sheer, incomprehensible power required to activate a warp field. When Miguel Alcubierre first published his groundbreaking paper, the initial energy calculations were not just large, they were obscene. To create a warp bubble just a few meters across his early models required an amount of negative energy equivalent to the total mass energy of the entire observable universe. Let that sink in. To propel one ship, you would need to harness the power of every star, every galaxy, every nebula, every black hole from here to the cosmic horizon. You would need to bankrupt creation itself for a single voyage. Of course, this was an initial, unrefined estimate. Physics did not stand still. Over the years, brilliant minds chipped away at the problem. They tweaked the geometry of the warp bubble, shaping it, refining it, making it more efficient. Physicist Harold Sonny White, working with NASA, proposed a new shape, a smoothed-out donut of warped spacetime instead of a flat-topped wall. This subtle change had a dramatic effect on the energy budget. The numbers began to fall. From the mass energy of the universe, the requirement plummeted to that of a single large galaxy. Still impossible, but a step in the right direction. Further refinements brought it down to the mass of the Sunday, then to the mass of the planet Jupiter. A breathtaking reduction, a triumph of theoretical physics. More recent, more speculative papers suggest it might be possible to power a warp drive with the mass energy of a large vehicle, or perhaps even less. It seems the problem of energy might just be solvable after all. Or is it we have become numb to the scale of the cosmos? We speak of planetary masses as if they were commodities, but we must remember what this truly means. Einstein's iconic equation E equals mc squared is the most fearsome and profound statement in all of science. Energy is mass multiplied by the speed of light squared. The speed of light is an immense number. Squared, it is a figure of almost divine proportions. It tells us that within even the tiniest speck of matter lies a reservoir of energy that beggars belief. Let us reconsider the optimistic estimate, the mass of Jupiter. This is not the energy you would get by burning Jupiter, like a log. This is the energy you would get if you took the entire planet, all 318 Earth masses of hydrogen, helium, and rock, down to the last atom, and annihilated it with perfect efficiency into pure energy. The resulting explosion would outshine our Sun for millennia. It would be a cataclysm visible from neighboring galaxies. This is the power needed not to run the ship for years, but simply to turn the key in the ignition, to create the warp bubble for a single moment. Sustaining it would require a continuous, ravenous consumption of fuel on a scale that transcends any notion of human engineering. The engine of a warp-capable starship would not be a machine. It would be a controlled singularity, a harnessed quasar. It would be a furnace that feeds on worlds. The infrastructure required to gather, store, and manipulate such quantities of energy is beyond science fiction. It belongs to the realm of mythology. We would need to build Dyson swarms around entire stars, not just to power our civilizations, but to fuel a single vessel. We would need to become masters of matter-antimatter annihilation on a planetary scale, a process so volatile that the slightest miscalculation would create a supernova. So even with the most generous theoretical refinements, the energy cost remains a barrier of cosmic dimensions. It suggests that warp travel may not be a technology for a young planetary species like us. It may not even be for a mature starfaring one. It might be reserved for beings so advanced, so integrated with the physics of the universe, that they can casually toss planets into their fuel tanks. For them, a starship's journey would be powered by the ashes of a solar system. Is this a price any civilization could or should be willing to pay? The second dragon has not been slain, it has merely been defined, and its sheer size is enough to cast our future in shadow. But the labyrinth of impossibility grows deeper still, for even if you could somehow conjure exotic matter from the void, and even if you could somehow summon the energy of a sun, the universe has laid more subtle, more insidious traps. These are not problems of engineering, but of logic. They are paradoxes that threaten to unravel the fabric of reality itself. The first of these is causality, the orderly procession of cause and effect that governs everything. I speak, and you hear. A star explodes and light reaches us later. Cause always precedes effect. Faster than light travel, however, breaks this sacred rule. According to Einstein's relativity, moving faster than light is mathematically indistinguishable from traveling backward in time. Imagine a destination 10 light-years away. Using a warp drive, you could theoretically make the journey in what feels like a week of your own shipboard time. But to an observer back on Earth, your arrival could be registered before the light from your departure even arrives. From their perspective, you have vanished from Earth in 2050 and materialized at your destination in 2045. You have moved faster than your own story. This opens the door to all the classic paradoxes of time travel. You could send a message back to Earth, arriving before you left, instructing your past self not to embark on the journey. But if you never leave, how could you have sent the message? The chain of causality is shattered. The universe descends into a nonsensical chaos of contradictions. Many physicists believe this is not just a philosophical puzzle. They suspect the cosmos has a built-in protection mechanism, a fundamental law which we might call the chronology protection conjecture that prevents such paradoxes from ever occurring. If this is true, then the speed of light is not merely a limit, it is a firewall. a universal principle that preserves the sanity of spacetime by forbidding any object or information from ever completing a journey into its own past. The dream of warp speed crashes against the immutable logic that effect cannot precede its cause. To travel to the stars, it seems you must not threaten time itself. But let's press on. Let us assume even this can be circumvented. Perhaps there is some unknown law that tidies up the paradoxes. A new danger now emerges, one that is intimate and terrifying. It is the problem of control, the paradox of the silent cockpit. Picture yourself as the pilot of a warp-capable vessel. You are encased in your bubble of flat, undisturbed spacetime. Outside, the universe is being contorted in unimaginable ways. But inside, everything is calm. You feel no acceleration. There is just one problem. The front of your warp bubble, the very region of spacetime that is being compressed to propel you forward, is causally disconnected from you. Light from that region cannot travel backward to reach your ship, because the space there is moving away from you faster than light. This means you are flying completely, utterly blind. You cannot see where you are going. You cannot send a signal forward to scout the path ahead. You are a surfer on an immense silent wave of spacetime, but you can neither see the wave's crest nor the shore it rushes toward. How do you steer? How do you navigate a course through an interstellar dust cloud or around an uncharted rogue planet if you are fundamentally incapable of observing what lies directly in your path? Even more perplexing, how do you stop to decelerate? You must send a command to the front of the bubble instructing it to cease its compression of spacetime. But if no signal can reach it, how do you turn the engine off? You might have to pre-program your entire journey, loading a destination into the drive before you even begin. But this assumes the universe between here and there is a perfect, predictable void. It is not. It is a dynamic, shifting environment. You would be a bullet fired at a target, light years away, helpless to alter your course, praying that nothing drifts into your path. During the centuries-long flight, the ship would not have a pilot, it would have a passenger, a prisoner inside a bubble of their own, making catapulted across the cosmos, with no view, no control, and no emergency brake. The very mechanism that enables your incredible speed simultaneously isolates you, rendering you a helpless projectile. And this brings us to the final and perhaps most terrible obstacle, a consequence so devastating it transforms your vessel of exploration into a weapon of unimaginable destruction. This is the problem of the bow shock. Interstellar space is not truly empty. It is filled with a tenuous mist of particles, stray hydrogen atoms, dust grains, cosmic rays. As your warp bubble hurtles through this medium, it acts like a cosmic snowplow. Particles that strike the front of the bubble do not bounce off. They become trapped in the intensely warped spacetime at its leading edge. They cannot enter the bubble because of its causal disconnection, and they cannot escape because space is flowing into the bubble faster than they can be thrown away. So they accumulate. With every light year you cross, more and more matter is gathered and plastered onto the front of your ship. But it is worse than that. Because of the extreme blue-shifting effects within the warp field, these particles are energized to impossible levels. A simple hydrogen atom is transformed into a high-energy cosmic ray. A speck of dust becomes a bomb of gamma radiation. Your journey becomes a process of silent, deadly accumulation. A cosmic charge is being built invisible to you, growing in power with every moment you travel. And then you arrive at your destination. You have reached Proxima Centauri, or the Andromeda Galaxy. You have achieved the dream, and now you turn the drive off. The moment the warp field collapses, all of that accumulated matter, all of that stored hyper-accelerated energy is released in a single, instantaneous, forward-facing blast. You do not simply arrive. You announce your presence with a sterilizing wave of radiation, so powerful it would vaporize anything in its path for millions of miles. Any ship waiting to greet you would be instantly annihilated. any orbiting space station obliterated. If you were careless enough to stop your journey anywhere near a planet, you would scour its surface of all life. You would boil its oceans and burn away its atmosphere. Your act of arrival would be an act of planetary genocide, the ultimate cosmic irony. In our quest to find new life, we would become its unwitting executioners. The starship, a symbol of hope and connection, is transformed by the laws of physics into a relativistic doomslayer. The hand we extend in greeting becomes a fist of annihilation. Here then, our journey into the dream of warp speed must pause. We stand before a trinity of insurmountable walls. The wall of matter, a requirement for a substance that seems to be a physical impossibility. The wall of energy, a demand for fuel so vast it requires the sacrifice of entire worlds. And the wall of paradox, a series of cosmic traps that threaten to shatter causality, strip us of control, and turn our explorers into accidental destroyers. The beautiful mathematics that opened the door to the stars has led us into a hall of cosmic horrors. The warp drive, once the gleaming hope of science fiction, is pushed back into that ethereal realm. It is a stark, humbling reminder. The universe does not owe us a path to the stars. The laws of physics are not suggestions. They are the silent, unyielding architecture of everything. And they may have built a cage not of iron bars but of energy, logic, and light itself. A cage from which we may never, ever escape. So we have come to the final moment of our cosmic trial. We have weighed the dream against the law, the phantom against the mountain. We have chased shortcuts through the very fabric of spacetime. And we have stared into the unblinking, unyielding glare of light itself. The question that has propelled us across this entire journey now demands its answer. Warp speed versus light speed. Which one truly wins? The verdict, stripped of all fiction and wishful thinking, is both sobering and magnificent. It is a conclusion written not in our scripts but in the fundamental code of the universe. The winner is, and perhaps always must be, the light. This is not a failure of imagination. It is a triumph of reality. The dream of warp drive, of bending space to our will, is a seductive spectre. It promises a universe without distance, a galaxy we can tour in an afternoon, but it remains a ghost in the machine of physics. It demands energies that beggar belief, forms of matter that may not even exist. It requires us to break the most fundamental rule we have ever discovered, the rule that says cause must always precede effect. To build a warp drive, we might not just be building a ship, we might be building a time machine, an engine of paradox. The universe, it seems, does not permit such casual vandalism of its timeline, so the dream of the shortcut fades into the glare of what is possible. And what is possible is a far grander, more arduous, and more noble challenge. The unyielding cosmic speed limit is not a prison wall. It is the ultimate mountain we are challenged to climb. We cannot break the law of light, but we can learn to master it. We can strive to approach that absolute velocity, to ride the edge of the ultimate frontier. This is the true path to the stars, a journey not of cosmic cheating but of supreme and sustained effort. It is a quest that will demand the greatest technology we have ever conceived. Engines born from the hearts of suns, fueled by the very essence of creation and annihilation. This is the story of how we will actually leave our cradle. To journey between the stars, we need a new kind of fire. The chemical flames that lifted us from Earth are children's toys in the interstellar void. They are a puff of smoke against the gulf of light years. We need an engine that taps into the source code of stellar power. We need to build a star in a bottle. This is the monumental promise of fusion propulsion. It is the process that powers our own sun and every star that glitters in the night. Fusion is the forced marriage of atomic nuclei under unimaginable heat and pressure. When light elements like hydrogen are crushed together, they fuse. They form a heavier element, and in that cataclysmic union a sliver of their mass vanishes. It is not lost, it is transformed. It erupts into a torrent of pure incandescent energy. This is the secret of the stars, the equation that holds back the darkness. E equals mc squared. Harnessing this process is one of the greatest technological undertakings in human history. Here on Earth, we build colossal machines, magnetic temples called tokamaks. Inside them, we attempt to replicate the conditions in the core of a star. We suspend a cloud of hydrogen isotopes in a ferocious magnetic grip. We heat it to over 100 million degrees Celsius, a temperature many times hotter than the center of the Sun. At this temperature, matter ceases to be gas. It becomes a fourth state, a seething electrified storm called plasma. The goal is to contain this celestial fury long enough for the atoms to fuse. To achieve ignition, a self-sustaining burn that releases more energy than it consumes. For decades it has remained just beyond our grasp, but we are closing in. Now imagine taking that star-forging crucible and attaching it to a spacecraft. A fusion drive would not be an engine of quick explosions. It would be an engine of continuous, relentless power. A magnetic nozzle, an invisible funnel of pure force, would channel the escaping plasma. This exhaust would be no mere chemical flame. It would be a stream of particles screaming into space at astonishing velocities, perhaps as much as 10% of the speed of light. The thrust would be gentle at first, but critically, it would be constant. Day after day, week after week, the fusion star would burn. The ship would accelerate without cease. Its speed would build hour by hour into a monumental velocity. Within months, it would be the fastest object ever built by human hands. A journey to our nearest stellar neighbor, Proxima Centauri, would be transformed. With chemical rockets, the voyage is a fantasy of 70,000 years. With a fusion drive, that chasm of time contracts. The journey could be made in 40 years. Still a long time, a generation spent in the deep dark, but it is no longer an eternity. It is a human timescale. For the crew aboard such a vessel, the universe itself would begin to warp, not because they were bending space, but because they were mastering speed. As they approached, a significant fraction of light's velocity time would slow down for them. The cosmic clock would tick at a different rate inside their ship. Their 40-year journey might feel like 35 years to them. A small difference, but a profound confirmation of Einstein's strange reality. They would return to an Earth that had aged more than they had. They would be travelers not just in space, but in time. The challenges are, of course, immense. How do you manage the tempest of radiation pouring from your own engine? How do you build a magnetic bottle strong enough to contain a miniature sun for decades? The scale is staggering. A fusion-powered starship would not be built. It would be constructed in orbit, a colossal edifice of magnets, reactors, and radiation shielding. It would be our first true ark, a self-contained world designed for the long night. But unlike the dreams of warp travel, the obstacles are those of engineering, not physics. The universe allows this. The blueprints are there, waiting in the hearts of the stars themselves. We simply need the will and the genius to build what we already see. But fusion, for all its stellar power, may not be the final word in propulsion. For there is a fuel source in the universe, so potent it makes a star's fire seem like a flickering candle, a substance so volatile its very existence is a paradox. To find the ultimate source of energy, you must journey to the boundary of existence. You must look into a mirror, a perfect reflection of our reality. For every particle of matter that makes up you, the Earth, the stars, there exists a potential twin, an antiparticle. It has the same mass, the same properties, but one crucial difference, an opposite charge. An electron carries a negative charge. Its twin, the positron, is positive. A proton is positive. The antiproton is negative. This is antimatter. It is the photographic negative of our universe. On its own, it is perfectly stable. An anti-atom could form an anti-world. An anti-galaxy could glitter in the void, indistinguishable from our own from a distance. But if matter and antimatter should ever meet, the result is total, perfect annihilation. It is not an explosion in any conventional sense. There is no fire, no chemical reaction, no shrapnel. It is a silent, instantaneous conversion. 100% of the mass of both particles vanishes, and in its place a scream of pure energy is born. A flash of high-energy gamma rays, the most powerful light in the cosmos. This is Einstein's equation made manifest in its most extreme form. The energy released from annihilating a single gram of antimatter with a gram of matter is equivalent to the detonation of the most powerful nuclear bombs ever created. It is the most efficient, energy-dense process known to physics. There is nothing more powerful. This is the ultimate fuel. An antimatter drive is the holy grail of relativistic travel. Its potential is almost difficult to comprehend. In theory, a ship powered by matter-antimatter annihilation could be astonishingly efficient. It would not need the massive fuel tanks of a chemical rocket. A few pellets of antimatter the size of grains of sand could propel a probe to another star. The engine itself would be a marvel of magnetic control. A stream of antiprotons, mere femtograms at a time, would be guided from their containment. They would be directed into an annihilation chamber to meet a stream of normal matter. The resulting blast of gamma rays and charged particles would be terrifyingly potent, so potent in fact that they cannot be directed by any physical nozzle. No material could withstand that onslaught. Instead, a powerful magnetic field would have to catch the charged particle debris. This exhaust, known as pion plasma, would be funneled out the back of the ship. The velocities could be astounding, 30, 50, perhaps even 70% of the speed of light. At these speeds, the journey to Proxima Centauri shrinks dramatically. A 40-year voyage with a fusion drive could become a 10-year voyage. And for the crew, time dilation would become a profound and life-altering reality. While 10 years passed on Earth, only 6 or 7 might pass for them. They would be sprinting toward the stars on a wave of pure, annihilated reality. They would arrive younger than their own mission clocks. This is as close to science fiction as real physics has ever dared to venture. So why have we not built one? Because if the potential is sublime, the problems are almost supernatural. First, there is the issue of production. Antimatter does not exist in nature around us. We have to forge every single antiparticle in our most powerful machines. At places like CERN, we smash protons together at nearly the speed of light. In the wreckage of these collisions, for a fleeting instant particle-antiparticle pairs are born. We can then trap the antiprotons with magnetic fields. The process is monstrously inefficient. The energy required to create a single microgram of antimatter would be enough to power a major city for a day. To produce enough to fuel a starship would require the entire energy output of human civilization, and it would take thousands of years. Then there is the second, even more terrifying problem: storage. How do you hold a substance that annihilates anything it touches? You cannot put it in a bottle. You cannot let it touch the sides of any container. The only solution is a perfect prison of forces, a magnetic trap. The antimatter held as a charged plasma would float in a perfect vacuum, suspended by powerful electromagnetic fields, never touching a single atom of the container wall. It is a bomb of unimaginable power, waiting for a single mistake. A momentary power failure, a flaw in the magnetic containment, and the ship would simply cease to exist in a silent, blinding flash of gamma radiation. The risk is absolute, yet the prize is equally absolute. A pathway to the stars within a human lifetime. An antimatter drive represents the pinnacle of brute force propulsion. an engine that consumes reality itself to conquer the void. But there is another path, a more elegant, more ghostly vision of interstellar travel, a way to journey not with fire but with the gentle, persistent pressure of light itself. It is one of the strangest ideas in all of physics. Light, the very definition of ethereal and massless, has momentum. Photons, the particles of light, carry a tiny infinitesimal push. When sunlight streams through your window, the photons are striking you. You don't feel it because the force is absurdly small. But in the perfect, frictionless vacuum of space, that tiny push can work miracles. Over time, that ghostly pressure applied without end can build to tremendous speeds. This is the principle behind the most elegant of all starships, the light sail. Imagine a craft with no engine, no fuel, no violent exhaust. Instead, it unfurls a vast gossamer membrane in the darkness, a mirror kilometers wide but thinner than a sheet of plastic wrap. It is a sail crafted from advanced materials, impossibly light, perfectly reflective. This is the ship. Its engine is not on board. Its engine is located millions of miles away, perhaps in orbit around our sun. It is a colossal array of lasers, a phased battery of light cannons, a system of unimaginable power focusing its entire energy into a single coherent beam. This beam, a river of pure photons, is aimed with impossible precision across space. It strikes the distant waiting sail. Each photon arrives, strikes the mirror-like surface and bounces off. In that reflection, it transfers a minuscule amount of its momentum to the sail. A single photon does almost nothing, but a torrent of them, a continuous blast from a gigawatt laser, is different. The sail begins to move. Silently, gently, it accelerates. There is no roar of an engine, no plume of fire. Just a craft of shimmering foil being pushed by a starbeam. The beauty of this system is that it escapes the curse of the rocket equation. A traditional rocket is a beast of burden. Most of the fuel it carries is used simply to accelerate the fuel it has not yet burned. Its efficiency plummets as the journey goes on. The light sail carries no fuel. Its engine is the laser far behind it. The craft itself can be incredibly light, a small robotic probe perhaps. And because the laser can shine continuously, the acceleration never stops. For weeks, for months, the laser pours energy onto the sail. The gentle push builds and builds. The sail's velocity climbs relentlessly. 1% of light speed, 5%, 10%. The models show that a powerful enough laser array could push a small probe to 20% of the speed of light. At that velocity, the journey to Proxima Centauri is no longer a generational affair. It is a 20-year trip. Our first emissary to another star system could arrive within our lifetimes. We could see images of its planets, taste the chemistry of its atmosphere. The dream of interstellar exploration becomes a concrete engineering project. Of course, the scale of that project is almost mythic. Building a laser array capable of generating that much power is a civilization-scale endeavor. It would require an energy source dwarfing anything we have today. The sail itself must be a miracle material, strong enough to withstand the laser's push without tearing, reflective enough to not absorb the energy and melt into vapor, light enough to be accelerated effectively. And then there is the problem of aiming a laser beam across 4 light-years. That is like trying to target a single bacterium from across a continent. The precision required is staggering. And perhaps the greatest riddle of all is the question of slowing down. The laser can push, but it cannot pull. How does a craft traveling at 20% of light speed stop when it reaches its destination? A head-on collision with Proxima Centauri is not the desired outcome. Several ingenious solutions have been proposed. Perhaps the sail could be divided into concentric rings. As it approaches the target star, the outer ring detaches. It continues ahead, reflecting the light from Proxima Centauri back at the main sail. This stellar light would act as a braking force. Another idea is to mount a smaller but still powerful laser on the probe itself. It would fire forward using its own light pressure to decelerate over many years. Or maybe the most ambitious solution of all, we would have to send a second laser array to the destination star system ahead of time. A colossal braking system constructed by robots waiting to catch our speeding probe. The complexity is breathtaking, the vision audacious. A network of lightways connecting the stars with beams of pure energy. Ghost ships surfing on photons, their gossamer wings catching a man-made wind. So we stand at the end of our inquiry, the question resolved. The dream of warp speed, of tearing a hole in the universe for our own convenience, recedes. It remains a tantalizing what-if, a ghost story told by theorists at the edge of physics. It is a hope for a magic wand in a cosmos that does not seem to trade in magic. What wins, what endures, is the rule of light. The reality of near light speed travel is our true inheritance. It is a future built not on breaking the rules, but on achieving absolute mastery within them. It is a destiny forged in the fire of fusion engines. It is propelled by the perfect energy of annihilation. It is carried on the silent, elegant wings of light sails. These paths are not easy. They are monumentally difficult. They demand more energy, more resources, more genius than any project in human history. The journeys will be long, spanning decades, even centuries. Those who leave may never see the Earth they knew again. But this is what it means to be a species that reaches for the stars. The universe does not offer shortcuts. It offers a challenge. The ultimate speed limit is not a barrier. It is an invitation to be brilliant, to be patient, to be bold, to build our cathedrals of science and engineering, and to set sail on the longest, most meaningful voyage we can imagine. The victory is not in arriving quickly. The victory is in the journey itself. We have reached the end of a cosmic marathon, a journey that has taken us from the familiar to the fantastical, from the bedrock of known physics to the very edge of imagination. We have raced two champions against each other across the expanse of spacetime. In one lane, a titan of reality, the universe's ultimate constant. In the other, a seductive dream, a promise of impossible swiftness. Light speed versus warp speed. The final verdict in this celestial contest is now upon us. And the truth, like the cosmos itself, is both beautifully simple and profoundly complex. The universe does indeed have a speed limit. It is not a suggestion, nor is it a rule that can be bent or broken. This ultimate velocity is woven into the very mathematics of existence. It is the pace of causality, the tempo to which every interaction unfolds. This cosmic metronome is the speed of light in a vacuum, 300,000 kilometers per second, a figure so immense it defies our terrestrial intuition. Yet on the galactic scale, it reveals itself as a stark and formidable barrier. It is the undisputed sovereign of our physical universe. When we peer into the night sky, we are not seeing the stars as they are. We are witnessing them as they once were captured in photons of ancient light. That light, traveling diligently across the void, is a time machine. It carries the history of the cosmos, a story told at a fixed and unalterable pace. This is the essence of light speed's reign. It isn't merely a velocity one can achieve. It is the framework within which time and space derive their meaning. As an object with mass accelerates, reality itself begins to resist. Time for that object dilates, stretching towards an eternity. Its mass escalates, approaching an impossible infinity. The energy required to push it further grows beyond all measure. The universe is not telling you to slow down. It is demonstrating that there is simply no more faster to be had. This isn't a finish line you can cross. It is the absolute boundary of the racetrack itself. The dream of warp speed was always about finding a loophole in this cosmic statute. a way to cheat the system to bypass the ironclad law of Einstein. The Alcubierre drive, in its elegant mathematics, offered just such a vision. It proposed not to move through space, but to move space itself, to surf on a wave of space-time, contracting the void in front, and expanding it in the wake, leaving the local laws of physics completely untouched. A vessel resting peacefully inside this warp bubble could traverse galaxies. It could cross unfathomable distances in the span of a human lifetime. It was a breathtakingly clever idea, a testament to theoretical ingenuity. It was the ultimate shortcut. But our journey has revealed the profound chasm between a beautiful equation and reality. The warp drive, this magnificent starship of the mind, runs on an impossible fuel. It demands exotic matter, a substance with negative mass and negative energy density. This is not merely something we haven't found yet. It is a material that appears to violate the known principles of energy. A substance that, if it could exist, might unravel causality itself. The energy requirements, even with this fantastical fuel, are staggering. They are astronomical in the most literal sense, requiring the mass energy of entire planets or even stars to get started. The paradoxes pile up, forming a mountain of impossibilities. How do you steer it? How do you stop it? How does the pilot inside communicate with the bubble outside? Every solution seems to breed a host of new, more intractable problems. So the contest concludes. Light speed wins. It is not a victory by points or by a narrow margin. It is a fundamental triumph asserted by the very structure of our universe. Warp speed, for all its allure, remains a ghost. A beautiful phantom haunting the star-dusted shores of science fiction. Yet to dismiss this dream as a mere failure would be to miss the entire point. It would be a profound misreading of how science truly advances. The quest for the impossible is never a waste of time. It is one of the most powerful engines of discovery we possess. The theoretical pursuit of faster-than-light travel has been a gift, a glorious, illuminating, and incredibly fruitful failure, because in trying to figure out how to break the rules of the universe, we have been forced to understand those rules with an unprecedented depth and clarity. It has served as a crucible for our understanding of general relativity, pushing Einstein's masterpiece to its most extreme and bizarre limits. When Miguel Alcubierre first formulated his equations, he wasn't just designing a starship, he was posing a profound question to the fabric of space-time itself. He was asking, what are you capable of? What contortions can you endure? The answer to that question has been a revelation. Physicists who grappled with the warp bubble's implications were compelled to explore the deepest mysteries of cosmology. The problem of negative energy pushed them to investigate the quantum vacuum, to study the subtle, ghostly fluctuations of virtual particles, to examine phenomena like the Casimir effect, where empty space itself can exert a real measurable force, a whisper of the strange physics required. It led to renewed inquiry into the nature of cosmic inflation. The moment after the Big Bang, when the universe itself expanded at a rate that vastly outpaced the speed of light. This wasn't a violation of relativity, but a feature of it. Space-time itself can stretch, and studying this primordial warp drive informs our models of the universe's origin and its ultimate fate. The investigation did not end there. The warp drive concept is a close cousin to another theoretical marvel, the wormhole. A tunnel through space-time, an Einstein-Rosen bridge connecting distant points. Like the warp drive, stable wormholes also appear to require exotic matter. They are also fraught with paradoxes and instability. But by studying them in tandem, by seeing how they are two sides of the same speculative coin, we learn more about the topology of space. We are forced to ask if space-time is truly a simple flat sheet, or if it might possess a hidden labyrinthine structure. with shortcuts and pathways that we cannot yet perceive or access. These are not idle questions. They probe the fundamental nature of gravity and quantum mechanics. They are essential steps on the path to a grand unified theory, a theory of everything that would finally reconcile the very large with the very small. Think of it like the ancient alchemists who sought to turn lead into gold. Their quest was based on a flawed premise, a misunderstanding of chemistry. They never succeeded in their stated goal, but in their relentless experimentation, in their obsessive pursuit of the impossible, they developed techniques for distillation, metallurgy, and measurement. They discovered new elements and new chemical compounds. They laid the foundational groundwork for the entire science of modern chemistry. The alchemists failed, but their failure changed the world. The theoretical pursuit of the warp drive is our modern alchemy. We may never transmute the lead of sublight travel into the gold of a warp bubble, but the intellectual furnace we have built to attempt the transformation is forging a new, more profound understanding of the cosmos itself. It is a cosmic crime scene investigation, where the crime violating light speed turns out to be impossible. But in proving the impossibility, we have fingerprinted the universe. We have learned the unwritten rules that govern its behavior. We have mapped its hidden architecture in astonishing detail. The dream of warp speed has been an invaluable tool, a theoretical probe we have sent into the deepest heart of reality. And the data it has sent back, filled with paradoxes and impossibilities, has been more valuable than we could ever have imagined. It has shown us not our future, but the true nature of our present, the intricate, majestic, and unyielding reality in which we are embedded. So where does this verdict leave us, we fledgling explorers of the cosmic ocean? Does the supremacy of light speed leave us marooned on our small terrestrial island? Is humanity forever caged by the vast uncrossable distances between the stars? The answer is a resounding no. To see the cosmic speed limit as a prison wall is a failure of perspective. It is not a barrier to our destiny. It is a challenge to our ingenuity. It is a fundamental parameter of the universe we must work with, a parameter that will shape our future in the stars in magnificent ways. It forces us to be smarter, to be more patient, to be more creative. It asks us to abandon the fantasy of brute force and instead embrace the elegant solutions that the universe allows. Our future in space will not be one of instantaneous gratification. It will not look like the popular fictions of galactic empires, where starships hop between worlds as easily as we cross a street. The real human journey into the cosmos will be something far more profound, far more challenging, and ultimately far more rewarding. Freed from the distraction of the impossible shortcut, we can focus our collective genius on the real possibilities, the grand projects that are consistent with the laws of nature. We can envision solar sails, vast gossamer-thin mirrors pushed by starlight itself, accelerating silent robotic probes on centuries-long voyages to the nearest stars, carrying the legacy of our curiosity. We can design fusion rockets that heat hydrogen to incandescent temperatures, propelling our ships to a significant fraction of light speed. Journeys to Alpha Centauri would no longer be millennia but decades. Within the grasp of a single dedicated human lifetime, we can perfect the art of hibernation, of suspended animation, allowing crews to sleep through the long interstellar night, awakening as their ship finally decelerates into a new solar system, entire generations removed from the Earth that launched them. This leads to the most majestic vision of all the generational ship, a self-sustaining world in miniature, an arc sailing between the stars, on a voyage that will last for 1,000 years or more. The inhabitants of this vessel would not be the ones who left Earth, nor would they be the ones to arrive at the destination. They would be the journey itself. A continuous lineage of humanity carrying a torch of civilization, across an abyss of space and time that we once thought impassable. This is not a lesser dream than the warp drive. It is a greater one. It is a dream not of technological magic, but of human endurance, of foresight, of courage, and of an unbreakable bond across generations. The true engine of our expansion into the cosmos will not be exotic matter. It will not be a bubble of distorted spacetime. The propulsion that will carry us to the stars is the same force that brought us out of the caves and lifted our gaze to the heavens. It is curiosity, an insatiable, relentless, unquenchable desire to know what lies beyond the next hill, beyond the next ocean, beyond the next planet, beyond the next star. This is the inexhaustible fuel of the human spirit. It is this drive that builds the telescopes that let us see to the edge of time. Instruments like Hubble and the James Webb Space Telescope are our first true faster-than-light machines. Not because they travel through space, but because they conquer time. They gather the ancient light from the universe's dawn, allowing us to witness the birth of the very first galaxies, a journey of 13 billion light-years undertaken from our own backyard. This is the elegance of working with the universe, not against it. We use the light which dictates the speed limit as our very vessel of discovery. This is the ultimate lesson of our epic race. The contest was never truly between two different methods of propulsion. It was a contest between two different philosophies of exploration. One seeks to dominate nature, to rewrite its laws for our convenience. The other seeks to understand nature, to listen to its secrets, and to become a part of its grand unfolding story. It is the latter path that has always been the true course of scientific progress. We did not learn to fly by commanding the air to support us. We studied the principles of aerodynamics and built wings in harmony with them. We will not cross the interstellar void by commanding space-time to bend to our will. We will study the principles of physics and build vessels that can make the long, patient, and extraordinary voyage. The cosmos is not a problem to be solved or an obstacle to be overcome. It is a text of unimaginable grandeur, and we are just now learning to read. Its laws are not a cosmic cage. They are the grammar of a language that describes reality itself, and our destiny is to become ever more fluent in that magnificent language. So we look up at the night sky no longer with impatience, but with a newfound sense of reverence and perspective. The stars are not impossibly distant destinations we may never reach. They are invitations. They are reminders of the scale of the universe and our place within it. They beckon us forward, not with the promise of an easy journey, but with the promise of discovery, of challenge, and of transformation. Our reach for the stars will not be a sudden leap. It will be a steady, determined, and multi-generational climb, propelled by the light of our own sun and guided by the light of distant galaxies. One breakthrough at a time, one probe at a time, one light year at a time. The race is not over. In truth, it has just begun. And in this race, the real prize isn't to be the fastest. It is simply to take part in the journey.